Thank you. With this title, I want to link two topics. At one hand, the dually flat geometry of information geometry. At the other hand, spacetime, a concept from Einstein's relativity theory, and especially spacetime in 5 dimensions. And the essence of my talk is to explain how you get from 3 dimensions to 4 to 5, and maybe more dimensions. Every slide has a title, so I only have 11 slides mentioned here. I will start with saying something about the dimensions, and then I switch to information geometry and the Weizenberg connection, torsion and properties. And then I come to extension from lower dimension to higher dimension. And at the end I have 2 examples. 2 examples, one which is quite academic and which is found in the proceedings of the conference. The other example comes from a recent publication in Entropy. So let us start with the dimension of our world. With one eye, you see only a 2-dimensional world. You see a picture in 2 dimensions. With a second eye, or by moving around, you notice that we live in a 3-dimensional world. But then came Minkowski and Einstein around 1900, and they claimed that the world is 4-dimensional. And it's just not a claim. There's, of course, a lot of mathematics behind that. And that mathematics, they called the 4-dimensional space-time. Okay? And originally, it was formulated as a space collecting events happening in 4-dimensional space. Now, position in 4-dimensional space, position in 3 dimensions we know. The position in 4-dimensional space, the 4th coordinate is denoted, I'm sorry, wrong button. Let me, oh, completely out of order. That's what I wanted, but yeah, very tiny. The 4th coordinate is denoted x0. And it increases linearly with time, just like all other coordinates, because if you consider free motion in special relativity, a free object just moves linearly with time. Okay? But then the question arises, what is time? Okay? And the problem one has is, and the surprise is that the constant c, which happens here, which appears here, is the speed of light. So that means the theory of Einstein is a theory about objects moving at the speed of light. Okay? And that's a little bit amazing. Are we moving at the speed of light? Then you wonder, what is time? Okay? And that's a very philosophical question. And the answer that one gives is a very practical one. Time is whatever that you measure with a clock. Okay? And so part of Einstein's theory is a theory about clocks, explaining what is time, what do you measure with a clock. Okay? And it turns out that to describe a clock you need a pseudometric. And that's how pseudometrics come in the geometry of space-time. Pseudometric, and you have the metric connection attached to that. And with that metric connection, you can measure relative time differences along the geodesic of a single clock. Now, I can skip this. My reference here is the Book of Singh. It's a standard book about special theory, about the special relativity theory. The restriction added to the theory, that's what I've written here, is that the tangent vectors should satisfy this positivity condition. You know, if G is a pseudometric, then this quantity could become negative. I follow the plus, minus, minus, minus convention. Many people follow minus, plus, plus, plus convention. There are always two ways to do that. And asking that this quantity is positive is the condition that motion cannot be faster than light. Okay. Now, many textbooks of relativity theory will make an identification between the x0 coordinate and time. And that identification is correct in the proper frame of a single clock. But in my opinion, you better should not make that identification, because two different clocks in relativity theory have different readings. And really different readings. The experiment has been done. An atomic clock going around the Earth with a plane shows a different time than a clock that stays at the airport and doesn't move. So the identification of x0 with time depends on the choice of clock, and you better do not do that. Okay. And the important point for me is that time is associated with clocks, and a clock is described by a pseudometric. Okay, let's go to dimensions. Quite soon after Einstein's work, Kaluza and also other people, they came with the claim that the world is not four-dimensional, it's five-dimensional. And again, there's a lot of mathematics behind that. And the mathematics says that the theory of Maxwell about electromagnetism, about light, simplifies a lot in 5 dimensions. So there's a good reason to go from 4 to 5 dimensions. Simply, mathematics hints you. The hint is believe in 5 dimensions and the calculations become much more simpler. And especially from a geometric point of view, because in 5-dimensional theory, the Ricci curvature of space-time vanishes. And one of the difficulties of Einstein theory, practical difficulties, is when you do calculations. Four-dimensional space-time is a curved geometrical object, and it's very difficult to do calculations. Okay? If you go to 5 dimensions, suddenly it becomes flat in the sense that the Ricci curvature vanishes. The idea, one idea around that, is that our world is flat in 3 dimensions and in 5 dimensions, but not in 4. I have 2 quotes here, quite small, written, that claim you find in the book of Wesson on 5-dimensional physics. The other quote is from Edward Witten, where he argues that Einstein was afraid of 5 dimensions. He didn't like it, and he was afraid of the consequences of a 5-dimensional world, although himself he went from 3 to 4 dimensions. But okay, 5 dimensions, what about higher dimensions? There has been a huge effort the last 20, 30 years, string theory, M theory, K theory, about higher dimensions, 10 dimensions, 11, 12. And these days the conclusion is that we don't know. There's no final conclusion found up to now. What's the relevance of these dimensions for my talk? Very simple. If I go to information geometry and I have a parameterized model, my point is the model can become simpler if you increase the dimension, if you add one or a few number of parameters. And that's what I now continue. Information geometry. For me, space-time is just a parameter space, a point X in 5-dimensional space or in 4-dimensional that are 4 parameters. And the geometry of space-time I can transfer to my model of information geometry. That's what one always does with parameterized models in statistics. So that's the only difference is that my focus is on the parameters and not on the statistical model. For instance, I could take probability distribution of the exponential family. That's not very physical. It would be more physical to take something like the density of a gas at a certain point in space-time. But anyhow, let me just take the very well-known example of an exponential family. Then we have a metric, which is Fisher metric, which is the second-order cumulant of those random variables f mu. And the connection is that I consider is the third-order cumulant, which is written here. And that third-order cumulant is the M connection in the book of Amari Nagaoka. And the reason I choose that is because we know that in the context of dually flat geometry, the M connection is the dual of the E connection, and both are flat geometries. Okay, and I want in 5 dimensions a flat geometry, and I will take something like this M connection, and the property of that M connection, the property I will use, is that it's a Weizenbuck connection. What's a Weizenbuck connection? It's a connection, the definition I've given here, it's a connection for which there exists a basis in the tangent bundle with vanishing connection coefficients. That's by definition a Weizenbuck connection. But another way to say is that the connection coefficients, capital gamma, are up to that extra g factor here, are the gradient of the metric tensor. Okay? And you can verify that the M connection of the previous slide satisfies this relation. It's a little bit of work to verify that the third order cumulant is related to the derivative of the second order cumulant. Okay? So a Weizenbuck, and you could say a Weizenbuck connection, that's quite trivial, because if you know that there is a basis in which the connection coefficients do vanish, why don't you take that basis and then you have a simple system? The point is, of course, that we start from 4 dimensions and want to extend to 5 dimensions. We already have a basis in 4 dimensions. And then there's only one way to take the 5th dimension. That's just orthogonal for the metric that you have. It gives me the 5th coordinate. And automatically, I'm looking for a flat geometry, but I'm not free in choosing my basis. And that's why I use a Weizenbuck connection instead of a trivial one. What are the properties of such a connection? Is that it can allow for torsion. That's a main difference with the M connection that I talked about before. And torsion has been discussed in the context of information geometry by Kurose, by Henmi and Matsuzoa. They coined the word SMAT, statistical manifold admitting torsion. Okay. And there are 2 recent papers I want to mention here. The paper by Jun Zhang and Gabriel Kahn in information geometry, a few years ago, and a recent preprint by Chalya and co-workers on the Weizenbach connection. But you should know already Einstein studied that Weizenbach connection and in trying to find models for his theory 100 years ago. So it's all old stuff I'm talking about. Okay, what are properties of that connection? You have that starting relation, the dual basis vectors. So if I lift the index nu by the inverse of the metric tensor, I get the dual basis vectors, and they have the vanishing connection coefficients. So it's quite simple transformation, and that means also that you know what the parallel transport operators are from one tangent plane to another. You can write them down explicitly, they are written here. So it's not difficult to work with it. Also, you know that there are conserved quantities, and they are given here explicitly. If I have a geodesic with affine parameter t, then the derivatives here multiplied with the metric tensor give me conserved quantities. And in 4 dimensions I have 4 of them. In 5 dimensions I have 5 of them. I have 1 additional conserved quantity. And then the question is, what is that conserved quantity? And the suggestions were, it's the charge of a particle, or it's the mass of a particle. And there are different approaches, and I will not make that choice. I will not say anything about that. In the paper of Zhang and Khan, you find the proof that, part of it I have in my notes as well. The connection is torsionless, even only if there exists a potential, such that the Hessian of the potential is the metric. And it's also equivalent with a Kodazzi coupling of the metric with the connection. Okay, let me now go to the essence. I hope I still have some time left. How many minutes? 3 minutes, so I'm going quite slowly. I want to extend from spacetime as known in the theory of Einstein to a hyperspace, 1 extra dimension. And I have a Riemann metric tensor given, and I can extend that to get a curvature-free model in 5 dimensions. I have some note here about notations, but let me skip that. And then you have a 5-dimensional model, and you neglect what happens in the 5th dimension to get again a description of what happens in the 4th dimension. And I need one proposition is that if I have 4 initial velocities in 4 dimensions, they will determine a geodesic if and only if I get the same value for the conserved quantities written in that way. Because you want a one-to-one relation between geodesics and initial velocities. Otherwise, you don't have that correspondence. Okay, then I just will take 1 minute for each of the 2 examples. I have here an academic example with singularities, and my point is that if you have a model with singularities, you can hope to remove those singularities by adding an extra dimension. And general relativity there are plenty of singularities, like the speed of light, the point particles attracting each other infinitely strong at Planck distances, black holes, Big Bang, and so on. And the hope is to describe those singularities by having a runaway in the 5th dimension. That's my academic example, and you start from some metric and you can go further and construct a Weizenbach. And it behaves as a dynamical system. which is described in the paper, so I can skip that and go to my last example, which is the sitter space, also 100 years old, which is a fair model of an empty universe. The sitter worked in Leiden together with Einstein. And the model, as you find it in textbooks, starts from the pseudometric describing time. But you can make an alternative description using a Weizenberg connection in 5 dimensions. And it's written down here. And if you are interested, you can look it up in my entropy paper. And that's my final slide, so I stop here.